Okay, so this is a number 4 of week 11 discussion about the real gases versus ideal gases. So they want to use a real gas equation called van der Waals gas equation to calculate the volume of neon gas, which is 1 mole. So N here, N is 1.000 mole, so 1 mole. And then the pressure here is 500 atmosphere atm, and the temperature is 355 Kelvin. Okay, so I guess my choice is now naturally, for me, the R must be 0.0821, or sometimes if you look at the 8206 atm liter per mole Kelvin, right? So that's the unit. So therefore, the volume must be has a unit of volume, that's the volume. Symbol is the volume is V in the unit of liter. So that's what I would have. And the ideal gas equation, using that, the answer is pretty simple. So let's do that. Okay, so here's actually equation that what is called van der Waals equation. I will explain it to you a little bit later, but let's do the ideal gas equation, which is a pretty nice equation. So for that, once again, PV equal nRT. So therefore, the volume that I know for the ideal gas must be nRT divided by pressure. So 1.000, 0.08206, 355 Kelvin divided by 500 atmosphere pressure. Okay, so by plugging all the numbers, and you will find out 0.05826 liter. Okay, so this is let's just call it an ideal. Okay, so this is the volume if neon behaves like an ideal gas. So what is an ideal gas? What is an ideal gas means ideal gas can be summarized into two terms. One, no interactions between gas molecules. No attractive interaction and repulsive interaction. Number two, no physical volume. Well, they call it excluded volume. Okay, so those are the two assumptions for the ideal gases. So van der Waals gas is interestingly trying to solve that problem, and by having this correction here. So there is a parameter. The pressure is modified into this term. There is an A, and A has something to do with the interaction parameter. Okay, when A is positive and the gas molecule has attractive interaction. Okay, and the B now here, you see the B, that's a volume correction, right? So the interaction parameter, this is like a excluded volume corrections of parameters. So to essentially to offer the meaning of the gas by offering them, yes, it can have an interaction, it can have certain kind of the physical volume as a gas. And here they show A has this parameter, and the B has this parameter. As you can see, B, which is a volume per mole, whereas on A, which is essentially A times n squared divided by volume, has the same unit as a pressure, so it has this kind of funny unit that you can see over here. So as long as you use the pressure in the unit of ATM and the volume as a unit of the liter, you will be all fine, right? So, okay, so I already solved the first problem, so let me use a blue one. So this is the first problem. What is the ideal gas equation? What's the volume? So that's my answer. So second question now is, let's try to solve this question here. Okay, so the pressure is 500 atm, and the volume is something that I need to figure it out. And then A, which is the numbers shown up here, and then N, which is 1.0, so 1 square, multiply V minus 1 times B is N, which is 1, R 0.08206, multiplied by temperature, which is 355. So now you can see this equation becomes a little bit more complicated to solve it here. Okay? And then I need to solve the equation to find what is the value for this. You have to solve for that, right? So there are many different ways to solve this one. The one that is recommended in this here can be following the hint. So let's read the hint that was provided here. So one way to solve this van der Waals equation is, for volume, is using the successive approximation. So what's that means? So let me give you an example. Okay. So here's an example that has something to do with a successive approximation. Successive approximation. And I also maybe call self-consistent method. Okay? So what's that really means? So I want to solve the equation for x, but x minus fx is 0. If somebody says, can you solve this equation for that? It could be something like looks ugly, like x squared log x multiplied by, I don't know, sine x squared plus 2 equals 0. So think about solving this massive ugly equation. Looks like this. Whatever it is essentially can be simplified. X minus certain x is 0. And now you start to change your perspective, saying this. What that really means is x is same as fx. So if I have an x values, plug it in, I can calculate fx, and that should give me the value of an x, and I can plug it in. So this is my initial guess, and then I can just keep on iterating until essentially you do this approximation or iteration until the numerical value of x is same as fx. Okay? So once it's the same, you can go repeat these measurements, and then they are self-consistent in this way. This value are self-consistent. So when you keep on repeating this, recurring questions, and they are self-consistent in this way. And then you find this, and therefore x value is found by numerical computation, right? Computation. So that's an idea about what when they say, can you solve this one by successive equation? So let's have a look at this. And so it depends on your ability to find out. So this one looks like this term is a constant and divide by this, right? So what I can rearrange the equation at the top here, saying that, okay, so what I can see here, I can rearrange that volume minus B equal 0.08206,355, and then 500 plus, which is what's the value of my A? Yes, so that's a 0.211, so 0.211 and 1 over V square. Okay, and then I am going to make this changes. So, okay, having this one, I'm going to move to the other side, right? So, therefore, by doing so, you need to change your sign like this, and then I can just tidy it up here. So, what do you see here? Volume is function of a volume, and you can do this self-consistent calculation until you find the value. So the value of the B, which is 0.0171. So, okay, so 0.0171, and that's a liter per mole, right? So liter per mole, and it was multiplied by 1. So it's actually this whole term is just a liter. And yeah, we are talking about the unit is liter here now. But once again, by looking at this equation, this volume and this term, which is a function of the volume, it should be the same. So we can start to compute. And what's my initial guess? The best guess is, so that's why it says that use an ideal gas law, get the preliminary estimate for the volume. So initial, my first volume is V, I guess initial V naught is 0.05826. Okay, so I am going to plug that in and compute this value. Right? So this is what I have here now. So one way to look at that, so now the equation up there is V is a function of the V, and the first approximation is 0.05826 liter. That's from the ideal gas volume. And then when you calculate the volume, that you will get the number, which is 0.06892. Okay, so then I am going to put that in 0.0682892 liter to once again compute this value, and then you will get 0.070609 liter. So, and that will be my also the gas to plug it in as a volume 0.070609 liter, and to compute the new value for the volume. And then you will find out that this is a 0.0700816, and you can put that in 0.070816 liter, and then recompute, and this the volume, that's 0.7708. So then, and then what you have situation now, after a few calculation, we finally reached a situation where volume is same as something about the volume functions. Right? So finally, I solved this the volume. So therefore, I solved the volume for van der Waals gas is 0.0708 liter by numerical solution using what is called successive approximation. Some people call this is a self-consistent method, and also known as iteration numerical method. Okay, so then now you can solve this one. So therefore, the new van der Waals gas that we can use is those values. So let's go back to the problem here. Explain why those two values are different. Okay, so that's a different value. So because of they have occupied a different one. So particularly for the van der Waals gas has a physical volume, which is their excluded volume. So this must be your this is what used to be an idealized gas. So therefore, you need a much bigger. So that's the V minus NB, and the whole thing, which is that's your V, right? So this is the van der Waals gas. So you need a van der Waals gas. So you need a much bigger volume than it should be now. So now also we can explain it to you saying that, okay, once I know my volume, the pressure is 500 atmosphere pressure, and so therefore the pressure correction is P minus A times N square over V square. So they are experiencing the reduced smaller pressure than the van der Waals pressure. So van der Waals pressure is smaller than what is known as a idealized gas pressure, and because of they are experiencing some no, I think that's not important. So I think that I do not want to talk about this way. I will just leave it this way, that the pressure correction, and this is an attractive interaction, A value is a positive, and that's how much of the reduce the pressure that they will have exert as an outside pressure. Okay, thank you for your attention. I just talked about solving this quite in a way, complex equation. The concept is simple, but for me to be able to solve this equation, get the value of the v, this is a nonlinear equation. And how do I do that? I just reorganize an equation in a form looks like this: x equal function of an x. And if you ever find that and the numerical solution comes in handy, it's very easy to be done until you have a value that the fx value and x value is the same, and then you keep on repeating, and I'm pretty sure you're going back and forth, and this is finally we got this relationship coming true, and that is what this value. So the van der Waals gas has a bigger volume because it counts for the actual physical volume in addition to the void volume that is actually used as if they are in the ideal gas volume.